Alright folks, so today we're going to take a look at the specific heat lab, and the whole concept of this is for us to try to determine the specific heat of some known substances, and I have some metal samples up front here, and then I'm also going to give you guys a unknown substance, which is a metal that we don't know the identification of. And by using some simple loss and gain of heat or energy from these items, we should be able to try to figure out what that is. So if you look at some of your specific heat equations or your latent heat calculations, some of the information that we need to determine how much energy is given up or gained by an object is to know the mass of the substance, to know the change in temperature of the substance, to know the specific heat of the substance, and or to figure out how many calories were gained or lost in a given system. So what we're going to be doing is we're going to put a certain amount of energy into some of these items. For example, this chunk of aluminum, we're going to put it in a pot of boiling water, we're going to get it up to a certain temp, and knowing its initial temperature, we're going to drop it inside of a so-called closed system. We also call a calorimeter. It's basically an insulated cup, and inside of this there is also water. You'll drop the hot piece of metal into the room temperature water, and of course the energy is going to move from high to low. So the higher amount of energy or temperature is going to be in the aluminum, so this high temperature is going to actually decrease, and some of the energy that is lost, or in theory all of the energy that is lost, will then be gained by the water inside of the calorimeter. Now, assuming that this is a perfectly closed system, there should be no energy lost to the surroundings. Now, our results may show that that isn't perfect, and the reason that that may not be a perfect exchange is the calorimeter itself potentially is not a perfect insulator. Therefore, some of the heat that is lost to the air and then again touches the outside of the calorimeter can be lost to the air inside of the room around us. But the whole theory does still hold true that energy cannot be created or destroyed, and the heat that is lost from one substance is definitely going to go somewhere. So our laws of thermodynamics aren't being overcome, or we're not doing some magical thing here. It's just that we can't create a perfectly closed system with the apparatuses that we have at hand. So the first thing we're going to end up doing, if you take a look at your specific heat lab, is there's a list in the data table for brass, copper, aluminum, tin, and lead, which as I go across here and take a look, this is our brass, this is our copper, this is our aluminum, this is our tin, and this would be our chunk of lead, and then the last one here is an unknown. So the first thing that we're going to do is we're going to try to get the mass of the water that we're going to heat up, which is the mass of the water that's in here, and then we're going to want to get the mass of the metals. Then we will mix some of these items together. For example, I'm going to put the aluminum inside of this boiling pot of water, and I'm going to get an initial temperature for the metal and an initial temperature for the water. So we will use these LabQuest as thermometers, which will give us quite an accurate reading. And then when we get down toward the bottom, we'll find a final water temp and a final metal temp, because even if this is at 90 some degrees and I take it out of here and I put it inside of the water that is approximately 20 some degrees, the 90 some degree chunk of metal is going to cool down, and the 20 some degree volume of water is going to warm up, and they're going to reach equilibrium at some point. And whatever that equilibrium is, we're going to be recording as the final water temp and the final metal temp. Then you can calculate a change in heat, and from there you should be able to actually calculate the specific heats of the metals. So we'll go from there. So the first thing that you guys are going to see in the data table is to record the mass of the water. Now the mass of the water is going to be the water that's actually inside of the calorimeter. We're going to be using 250 milliliter samples of water. So if we measure this out to be exactly at 250 milliliters, we know that the density of water is equal to 1 gram per milliliter. So every time I add this into our calorimeter, we're going to find out that our mass of water is going to be equal to 250 grams. So if you want, you could fill it into the data table all the way across for brass, copper, aluminum, tin, lead, and the unknown. The second thing that we're going to do is we're going to try to find the mass of the metals. So for the metal masses, I'm going to take all the samples that I have, and I'm going to place them on the scale one by one and actually determine what their masses are. Now I told you that these are all the same mass, and they're extremely close, but they are not exactly the same. So I'll get the scale near the mass of all of these items, and I may have to make some subtle adjustments as we go. So they're all approximately around the 29 gram or 28 gram mass, I'm going to put this over here. I can just show you that if I tip this to 30, this is 30 grams, and you'll see that it's a little bit too much. So I'm going to back it back off to 20 and go to, let's see where we're at here, 29. And you can see that's a little bit less, and I'll slowly increase the mass here. So we're going to do this for all the metals, and we'll record that in the following screens. I'll show you actually all of the data for the mass of the metals. So here's aluminum right here. Perfect. Now we can record all the masses in the data table. So here you can see that I recorded all of the water mass and the metal mass for both the brass, copper, aluminum, tin, lead, and the unknown. So remember, all the way across we have the mass of the water being equal to 250 grams because we had 250 milliliters of water. Now the mass of the metal for the brass we had 29.0 grams. For the mass of the metal for the copper we had 29.05. For the aluminum we're at 29.1 grams. The tin is at 29.2 grams, the lead was 28.8 grams, and the unknown substance is 29.05 grams. So the next part of the experiment, we're actually going to be recording quite a few things. We're going to get the initial water and metal temperatures, and also the final water and metal temperatures. And the way that we're going to do that is inside of this boiling pot of water, we're going to add our first sample. So I'm going to go over here and I'm going to grab the brass. So this is our brass sample that we had. I'm going to put the brass inside of the boiling pot of water, and I'm going to give it some time to heat up to temperature, but I will be using this digital digital meter here. It's a probe, a LabQuest probe, and I can place it inside of the water. And I'm going to kind of gently stir it around, kind of keep everything moving in there. I don't want to be measuring the temperature of the bottom of the pot necessarily. And you can see on here the temperature is kind of increasing as we're getting up to temp. We're going to be in the 90-some temperature range. And then inside of our calorimeter, we're also going to measure the temperature here. So you can see the air temp in here is about 21.3, and the water temp is approximately the same right now. This will change a little bit as we change our samples out. So as I warm up the water, I'm going to have new samples, 250 milliliter samples that I'm going to put inside of the calorimeter to go. So as we do that, we'll come over here and I'll give you guys the initial water temps, metal temps, final water temps and metal temps, and then the other calculations we'll be able to do on our own. So this is the one that we're going to have for brass coming up just next. I'm going to give this a minute to warm up so that they reach equilibrium, and then we'll do the transfer. Alright, I've given this some time to get up to temperature, and I'm going to stir this around a little bit and let the water temps get up to where we want them to be, and I'll get that reading down here. But prior to doing that, I got to try to make the transfer as quickly as possible into the calorimeter and try to get the insulated cover onto it. So I'm going to take our sample out of here, make sure it gets switched around. I'm going to drop it inside of the calorimeter. I'm going to cover it up, and we're going to get the temperature probe in here as quick as we can, and we'll let that slowly come up to temperature. So you will see that the temperature does start to increase on here, and we'll get you guys the data that you need here in just a second. Alright folks, so I just got done getting all the data for our first sample of brass, and our initial water temperature here is a little hard to read. I got 18 degrees flat, and our initial metal temperature when I was taking it out of the boiling water was at 96.2. The final water temp and the final metal temp, of course, are the same because those items have reached equilibrium, and they're both at 18.9 degrees. So I'm going to continue this pattern for copper, aluminum, tin, lead, and the unknown, and then we'll talk about doing the calculations down below. So we'll add all the rest of our samples here. We'll speed up the process a little bit now. I'm going to add all of the other ones here. I'm going to add the copper, aluminum, the unknown, don't want to tell you what that is, and the lead, and the tin. We got all those in there. We're going to let them boil up, and then we're going to start doing the switcheroo. We're going to remove some of the old samples and put those off to the side. We're going to change out the water in the calorimeter. I'm going to add my new 250 milliliter sample out of here, and we'll get different initial temperatures for water and initial temperatures for the calorimeter here also. So give these a chance to heat up and we'll come back to them. Alright, so we got the metals back up to temperature, and our next selection here is going to be copper. So I'm going to reach in here, I'm going to get the copper one out. There's the copper one, stir it around a little bit, plop it into our calorimeter, cover it up, get the probe in here, and remember these hot pieces of metal, all of the energy is going to be flowing out of those into the water. This is going to keep it as insulated as we can here, and we're going to record some of our temperature changes. We're going to record some of our temperature changes down here on the LabQuest. So, alright, we'll let these get to where they are, and we'll record some more data. There's the aluminum, drop that in the pot. Cover it up as quick as we can. Next up we got the tin. Get the tin out of here. Drop that in the calorimeter. Get it covered up. There it is. Next we got lead. Got the lead coming out of here. We got the lead in the calorimeter. And the last one here is our unknown. So this is going to be the unknown metal. We'll get that in there and we'll get that covered up. And we'll have the data to follow. Alright, so just to review the data that we did get, here's our initial and final water and metal temps for brass, copper, and aluminum. So going all the way across here, we had a consistent 18 degree starting temperature for our water, and that all came from the same major water source. Our initial metal temperatures did vary a little bit as the pot was kind of heating up and cooling down. So the brass we had at 96.2, the copper at 97.1, the aluminum was at 97.3, the tin was at 97.2, the lead was at 97.7, and the unknown was at 97.1. Then the next thing we're looking at is the final water and metal temperatures, which of course are the same because again they would all reach equilibrium. The brass we already had both at 18.9, the copper got to 18.8, the aluminum made it to 20 degrees, the tin went to 19, the lead went to 18.3, and the unknown went to 18.8. So that's kind of what your data should look like for this portion of the lab. Now you are going to see that there's some other things down here for us to calculate or figure out. The first one is the change in water temperature, and the next one is the change in metal temperature. So in order to calculate the change in water temp, change in metal temp, you're simply going to take the final temps of the metal and the water and subtract it from the initial. For example, if I'm doing the change in water temp for the brass, we ended at 18.9 degrees and we started at 18. So if I subtract the final from the initial, I get a change in water temp for the brass to be a positive 0.9 degrees. So it did increase by a whole lot, but remember we had 250 grams of water, which is quite a bit more than the mass of the metal. If I scroll down and take a look at how to calculate the change in metal temp for the brass, this is going to be the change in temperatures for just the metal. So the final temp for both the water and the brass, of course, are the same. They're both at 18.9 degrees. However, the initial temperature for the metal in this one was 96.2. So there's a much more dramatic change in temperature. Notice that this one's a negative because, of course, we started at 96.2 degrees and it decreased to 18.9. So we had a change in temperature for the brass to be negative 77.3 degrees Celsius. To calculate the heat loss or gain, which should be the same, and the specific heat of the metals, you're going to do the following. To calculate the change in heat, we're going to use the information for the water. So we're going to measure directly how much energy was absorbed by the water, not how much energy was lost by the metal, even though these numbers should, in theory, work out to be the same. To do this, you follow your latent heat equations. Change in heat is equal to the specific heat multiplied by the mass in grams, multiplied by the change in temperature in degrees Celsius.
Now, our specific heats, we're using calories per gram degree Celsius. So for water, we got 1 calorie per gram degree Celsius. The mass of our water is 250 grams, and the change in temperature here was 0.9. If I multiply all those out, I get a heat gain for the water to be 225 calories, which means the heat loss for the metal would be equal and opposite. It would be negative 225 calories. Now, how do we find the specific heat of the metal? We take the same equation and we rearrange it and we solve for specific heat. If I do that, I get something that looks like this. Delta heat divided by the mass times change in temp. Now all of these have to be relative to the metal. Fortunately, the change in heat is the same. However, the mass and change in temperature for the metal is not the same as the mass and change in temperature for the water. So we have to use that information as recorded in the data table. So the energy that is gained or lost in the process is the 225 calories. The mass of the metal, in this situation the brass, was 29.07 grams, and the change in temperature for the brass was 77.3. If I multiply, or take the number on the top and divide it by the value on the bottom, already multiplied together, so follow order of operations, because these two on the bottom, you need to get a sum or a product there first and then divide, gives me approximately 0.1. So this is all of what I'm going to be recording inside of my actual data table. Now this is just an example. I'm going to have you guys do all the rest on your own. Let's see what we got here. So our change in water temp for the brass was 0.9. Our change in metal temperature was the negative 77.3. The change in heat or exchange in heat for all of this is 225 calories, and then the specific heat that we got here at the very end was 0.1. So you guys should take the rest of the information for copper, aluminum, tin, lead, and the unknown and answer those questions below. You can also get more of the conclusions, answer some of the questions based upon some of the concepts explained in this lab will all be in the digital submission, so that will be part of completing the lab and getting it turned in. So thanks a lot, folks. I hope you guys all have a good day, and if you have any questions, please feel free to let me know, and we'll go from there. Thanks a lot.